what is our goal here? Let's take a step back. What we want to do is that for a given system with as many forces as apply to that system or at that body, and multiple couples, different couple moments, we want to simplify a system, right, with all these forces and couple moments and everything on them, to one simple system that has only a force and a moment. So we want to go from a body, a rigid body, that a bunch of forces, a bunch of couple moments are applied to it. We want to simplify that, or find the equivalent system of that system. We want to represent that system with just one force and one moment. And if we can, even with just one force. We'll see later on. Now, how do we do that? To do it, first we have to be comfortable with principle of transmissibility. Now, what does that say? We start talking about principle of transmissibility. I said principle of transmissibility tells us that if you move a force is a vector, right? If you move a force applied to a body at a specific point on a body, like a rigid body of some shape, the force is applied to a point. If you move that point, or that force, sorry, along the line of action of that force, you are not messing with the equilibrium. Basically, you're allowed to do it without changing anything about your rigid, your free body diagram. Let's say you have a free body diagram. There is a force applied to a specific point on your body, or you have a body, a force is applied to it. You can move that force along the line of action without being concerned about anything changing regarding your system. So you're allowed to do it with no concern, with no additional, with nothing. It's the same system. System would be the same. Basically, as they say, force is a sliding vector. You can slide it along this line of action. But we start with the last thing I mentioned was that what if we move the force out of its line of action? What if we have something like this pen? You can think about it as a rod. A force applied to it on this like end. What if we move this force? Well, this is the line of action for this force. Apply to this point. If it's in this point, this is the line of action. Now, what if I move this force not along this line of action, but out of its line of action? What if I move it from here to here? What if I go from here to here? This is the line of action. So I'm moving it out of its line of action. What happens then? We said if it's in line of action, don't worry. You're not messing with anything. You can basically, the system is still the same. It's the same system as long as the force is sliding along this line of action. When we move the force out of the line of action, out of its line of action, we can move it from this point to this point. Right? You can do it, but under one condition. What happens is that when force is moved from here to here, it creates a couple. F, this is the force, times the distance you move. Remember, couple was FD. In order to keep the system the way it was, to have the same system when you move, you have to add a couple to counter effect the couple created because of this motion. All right, let's see what I'm trying to say. Let's say, let's draw what I just drew. Let's say I have an object like this. It's straight attached to some fixed point. And I have a force F applied to it. I can definitely do better than that. Force applied to it, F. If I move this F all the way to the end or somewhere d distant d amount away from where it was, because of this motion, right, let's say I do this. I do this. I move it here. I'm moving the force out of its line of action. To have a system that is equivalent to the first system, right, I have to compensate for that motion. Let's say this one. And the way you can think about it is that I have to, this motion going from here to here, and this is where the force was. This is where the force was. And this is F. Now, if I move it d amount, right, let's say this is d. I went from there to here. To keep this system in the same condition, to make sure that this is the equivalent of the first system, I have to take into account, I have to add a moment to make it the same as it was. So this system right here, let me see if I can explain it. So this is the, let's say this is creating a force. This is the point we are going to move the force to. And this is distance d. So when we move this force, what happened is that to get the equivalent system, we have to add a moment there, right here, m. And this moment is Fd. Because that's the moment created by, let me do it in the same color as that one. This is the moment created by force d because of the translation d out of its line of action. Right. So we have a system force applied to it. Right? To get the equivalent system, if we move the force out of its line of action, what we're going to do is that we have to add a moment to the system to compensate for that translation. Think about this one. This is here. This is force applied to it. Right? Because of this force, you see this is trying to bend. Right? This is the moment created by this force around point, this point, M. Right? This F create a moment here around this point. But if I move it to the point, to that point, then this moment is gone. There is nothing to create the moment. So you can think about that as when I move this, I'm eliminating the moment this force is creating about this point. When I move it to this point, it means I have to compensate for that by adding the moment right here. So this is the equivalent system. M is equal to Fd. If I have this system, that's not what I wanted to do. If I have this system, the equivalent of that, if I move the force out of its line of action, would be the multiplication, would be the system with the force in the new place and added moment, which its magnitude is force multiplied by the distance I moved the force from the old point to new point. Let me see if I can put it in words what we did here. So you can write it this way. You can say force F can be moved, right? What we did there. Force F can be moved. Let's say it this way: provided that couple moment M is added to maintain, so we're putting it to maintain an equivalent system. Now, this couple moment, how can we find it? This couple moment, it can be found by taking the moment of F, where F was, about point B, right? This couple moment can be found by taking the moment of, from the moment of, let's say, F about the point where the force is moved. So M basically becomes a moment, and since it's a moment, it's just a free vector. It can be anywhere, but that's how we can find it. Remember, going back. So this is the idea. We said we're talking about principle of transmissibility, and we said principle of transmissibility is something we cannot prove. It's just based on experience. If the force is moved along its line of action, don't worry about it. You can move a force along its line of action without being worried of making any alteration in your system. If you move the force out of its line of action, you have to add a moment to the system to make sure that it's still the same system, to make sure that it's the equivalent of the system that it was. Then that moment is found by multiplying the force and the distance between where the force was and where the force is. I remember, since it's a moment, that's the perpendicular distance, right? So moment is the perpendicular distance. So we're finding, if this is where we are right now, and we're going from this to this one, right? We have to find the moment by multiplying the force and the distance the force moved from where it was to where it is. And that distance, perpendicular distance, right? It's a moment, so it should be perpendicular distance.